Hello, friends. We're going to talk a little bit about implicit differentiation. So we all know our derivative rules, and we know how to differentiate a function y with respect to x. And we're used to seeing functions y written explicitly in terms of x, right? So normally we have y equals and then a bunch of x's on the other side. But today we're going to talk about implicit equations. So if you look at the second equation I have here, y squared plus 3xy minus the square root of x plus 10 equals 8x, how do you define that explicitly? Can you isolate the y value? And of course, it's pretty difficult to isolate the y value. So in this situation, since it's hard to isolate the y value, we can say that the function is written y implicitly in terms of x. So this is an example of an implicit equation. So in order to differentiate implicitly, so we're going to talk about differentiating implicitly. So the operations that we're going to do in order to do this is going to be one, is we're going to take the derivative on both sides with respect to x. Okay? So when we do that, an example like d dx of 3x squared is 6x. But what about d dx of 3y squared? So we can still take the derivative, but we're taking the derivative of y with respect to x. So what we're going to do is we'll say this would become 6y, and then we write dy dx. So essentially the main difference here is just if you take the derivative of y with respect to x, you need to write dy dx at the end. So hopefully you can see the difference here. I took the derivative of x and it worked just as usual. But when I take the derivative of y, I still take my derivative as usual. This became my 6y, but I must write at the end dy dx that says I took the derivative of y with respect to x. So we want to find the derivative if we're given this implicitly defined function. So we're going to find dy dx if y squared equals x squared plus the sine of xy. Now, I really want you to understand why this is implicit, because how are you going to isolate that y there, right? Both the x and the y are in the argument of that sine operation. So to start this off, I'm going to take the derivative with respect to x of my function. Y squared equals x squared plus the sine of xy. So the derivative of a sum, or the derivative of each of these terms, essentially what we're going to be doing is we're going to spread that out or distribute that operation. D dx of y squared equals d dx of x squared plus d dx of sine of the argument xy. So we have three terms here. We're going to take the derivative of each. So the first term, taking the derivative of y squared, that's going to become 2y. But because I'm taking the derivative of y with respect to x, I write dy dx at the end. So moving along, for x squared, that derivative is 2x. And I don't have to write anything at the end because I took the derivative of x with respect to x. In a sense, you could almost think about it like I've got dx here. I took the derivative of x with respect to x. The derivative of x with respect to x. Okay? So anything over itself is equal to 1. All right, now we need to take the derivative of sine xy. And looking at this, we're going to have to use the chain rule. So the derivative of sine, as we all know, is cosine. So I've got the cosine of xy. However, by the chain rule, I need to take the derivative of that argument on the inside. All right, so the derivative of the inside, I'm just going to look at this piece right here. And this is the product of x times y. So I'll come over here as my scratch work. d dx of xy, using our product rule, that's going to be the first, which is x, times the derivative of y. The derivative of y with respect to x is dy dx, plus the second, y, and then the derivative of x is just going to be 1. Okay? So what I have here is 2y dy dx equals 2x plus the cosine of xy multiplied by x dy dx plus y. So at this point, our derivative is done. We've done all of the calculus, but what we need to do is isolate the dy dx, all right? So the derivative is done, but we want to isolate dy dx. All right, so we're just going to run through some algebra here. Because this cosine of xy is multiplied by all of that, I'm going to need to distribute. Okay, so all of this is going to have to go to both of those terms. So I'll rewrite this. 2y dy dx equals 2x plus x times cosine of xy dy dx plus y times the cosine of xy. Right, so I distributed cosine xy to both of those terms in my square brackets. So now this term can go to the other side of the equation, which gives me 2y dy dx minus x cosine xy dy dx. So that moved to the left, it became a minus. And then I have 2x plus y cosine xy left on the right side of my equation. So this moved to the other side of the equal sign and became a minus. And then these two pieces, the 2x and the y cosine xy, they stayed on the right side of the equal sign. So our second to the last step here is we're going to factor a GCF. And if you look now on the left, both of my terms have a dy dx. So I can pull that out as a GCF, dy dx equals 2y minus x times the cosine of xy equals 2x plus y times the cosine of xy. And then our last step would be to divide on both sides, isolate that dy dx, and simplify if possible. And in this situation, there really isn't much more simplification. I'm going to end up with 2x plus y cosine xy divided by 2y minus x cosine xy. And that, my friends, is our final answer. That is my implicit derivative. That is the derivative of y with respect to x.